Hello everyone. So this is the extra session for the course An Introduction to Cardiovascular Fluid Mechanics. And in this session we will be actually revisiting all the concepts that has been taught in the 4 week of this course, starting for the first week where this introduction to the fluid dynamics and then introduction to the solid mechanics and how this fluid dynamics and solid mechanics together helps in understanding the 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 flow of the blood, which is this the course name suggests an introduction to cardiovascular fluid mechanics. So how these cardiovascular events are related to the fluid mechanics and the solid dynamics, solid mechanics, right? So we will be gradually starting with the first week. I will be actually reminding all the concepts briefly, and we will be revisiting the questions that we have solved, and we will be meanwhile solving the assignments that has been discussed with you also, the assignments for 2025, along with the content that we have already discussed in last practice sessions. And what I think this entire course has helped you, and this particular lecture will help you in order to sharpen some of the concepts that need to be worked upon, right? So like starting with this, I just want you to uh, just focus on. So let me just present my entire screen, right? Yes, so just share it. Yeah. So this is this course, an introduction to cardiovascular fluid mechanics, offered by Professor Raghavendra Gupta, professor in Department of Chemical Engineering, IIT Guwahati. And as a part of Swayam course, this is like research topic. So this is research related course. And let me just connect my headphones so that things are okay, right? Just connected. Yes. Hello. I hope everything is okay now. Yeah. So it is connected. And this particular course, I am in presentation mode, right? So this particular course, let me just open the content which was there. Yes. So let us begin with this. So this course, an introduction to cardiovascular fluid mechanics. If I can open it in big screen, yes. Here, this you can see this course content for the all the 4 weeks, starting from the week 1 to week 4. Week 1 was this where you started with an introduction to the course, and then there was this fluid mechanics review, so that you just get reminded about the fluid mechanics. And there are like wide range of audience, not specifically belonging to the domain where this fluid mechanics is taught as a subject. And solid mechanics a review. Okay, and the week 2 we started with this rheology of the blood, then blood morphology, and then this let me just put it in this way so that I can look at. Yes, it's okay. So let us just put that over here, if we can do that. Yes. Yes, so it is okay. And where is this? And in the week 3 there is this viscoelasticity. As you know, this whatever cardiovascular system is there, there is this deformation of wall, this deformation of ingredients of the blood. We will be talking about the ingredients of the blood. What are those cells like WBC, RBC, platelets, and this plasma? What proportion of each makes this blood, and why this blood is having unique property? We will be discussing the same in a while. So week 3 was discussing about viscosity, flow bifurcation, pulsatile flow, beginning, and then week 4 was entirely for the pulsatile flow and this flow in the elastic tubes, right, where this Wormersley and everything came into the picture, right? So if you see this, uh, this entire course was structured in a way that you are actually working at the physics, I mean this fluid dynamical influences which is actually leading to some phenomena which is happening in our biological system, right? So the course started with, let me just now focus on the slides, right? So let us, yes, so the course prerequisite was nothing, just the students are suggested to review. So basic concepts of viscosity, fluid property, Navier-Stokes equation and its derivation you are supposed to be ready with while starting this course, designed for the engineering with background in the basic fluid mechanics. That was the sufficient thing. And this equation we have used many times in the course. So I will be just checking if I can highlight. So this particular, so if I can, hmm, okay, so what happened? We just see, like this is extra class. I think very less students. Like, anyway, these lectures will be recorded, so you can, we just on why this. So let us just make it, yeah. Okay. In the next part, there was this explanation on this, where this cardiovascular system is being explained, also called cardio circulatory system. The system includes where this series of tubes, which is this blood vessels, fluid. Here our fluid is blood, and this the pump, which is I mean this hematodynamics, like pumps, which is heart. Pumping is done by heart, as we know. Okay, so let us make it half. Okay, so if you see, let me just expand it. Yes. So this hematodynamics is what? This is the study of the blood, right? And then this cardiovascular system, uh, how it functions, what is the function of this, like nutrition transport. In the nutrition, basically you are transporting oxygen, amino acids, electrolytes to the body tissues, right? And then this, the transport to waste products, cellular waste, CO2 away from for excretion. So that is the another part of the story, right? And then the transport hormone from one part of the body to the other. It maintains the visceral organs, which is the internal organ, at a constant temperature. So that is another function of this. Hormone transport is happening, waste product transport is happening, nutrients transport is happening, and then this visceral organs temperature maintenance is happening. So these are the functions of cardiovascular. And then from a chemical engineering perspective, all the functions involved, what are the, on this we had one quiz question also in our some of the quizzes, right? So air fluid flow, which is this blood flow, heat atom transfer between the body at the constant temperature, mass transfer, which is this gas and the nutrient exchange, right? So if you see this and if you focus on this, so let me just see where I am on. So if you actually look at the link here, PDZ VKQQ HZP, right? Let me just check. Like nobody has joined till now. Maybe anyway, these recordings will be there. So say this is the right link, no problem. Okay. So anyway, and mass transfer is the transport of gas, the nutrient exchange, right? So if you see this cardiovascular system, it is consisting of two parts. One is this systemic, uh, one is this systemic circulation, and another is this pulmonary circulation. So if you are actually worried about this, let me just make it easy. Suppose this is systemic circulation, right? So what I'm saying is, if you see this is systemic circulation, what it does, first you see pulmonary circulation. What pulmonary circulation does, it supplies blood to the lung. So our lung is getting blood from the pulmonary circulation, and it is right heart's blood. So right hand side, so you know your heart is left hand side, and right his side is the mostly the lung, and right hand side part of the blood is nearer to the lung side, vast area of lung side. That's why it pumps, supplies the blood to the lung, right? And systemic is what? It supplies the blood to all the tissues except lung. So why? Because pulmonary is the one where this lung is covered, and lung is actually major area, also known as greater or peripheral circulation. So this is also known as systemic circulation, is also known as greater or peripheral circulation. It is the greater one. Why? Because most of the organs are being supplied. The left heart is working over here, right? So if you see this, so this is heart. Here it is 7%. Blood is in the heart, and then arteries 30%, arterioles and capillaries 7%, 7, 13, 7, and 64% is 64%, right? And you say 9% is the pulmonary circulation. So 9%. So if this percentage, based on this percentage, also some questions can come that ki, how much amount is at a time is in this deoxygenated side. So where is the largest one? So this venous, venules, and the sinus. Here, this 64% of the blood resides, which are deoxygenated one, which is in this uh, in the process of pumping of the blood, right? So if we go to the next slide, you see this. systemic circulation. So in the systemic circulation, it supplies in rest of the part of the blood except lung, and what left part of the lung works. Okay, so if you see, it is the red one. Red one is these, which is systemic circulation. So here, oxygenated blood pumps through the left ventricle. So left ventricle means what? Left ventricle, left side, right? And then supplies to the aorta, okay, through the carotid valve, okay. Then from the aorta to the different arteries, arterioles, and capillaries, it goes, okay. So as it is systemic, throughout the body it has to go. So arteries, arteriole, capillaries, blood goes to various part of the body. The gas and the nutrition exchange happens in the capillaries, right? So that is the another thing. From capillaries to the venules, right, and to the veins, right? So now from the capillaries to the venules and to the veins, blood goes into as right ventricle, right? From where? From left to right ventricle through this tricuspid valve. So this valve can be the one. So two things I have told you in this slide that can be important. One is this: which valve is the transition point from left ventricle to the right ventricle? Which valve is used? Which is tricuspid valve, and these percentages, like for pulmonary circulation, 9% of the valve is there, blood is there at a time, and then this heart 7%. So if you see, this discussion was also there, and if you actually look at the discussion carefully, so the left part of the heart is pumps the blood in the systemic circulation. Okay, that is, it supplies blood to all the part of the vessel to body, and lung is not there. And if you see this here, I'm saying is, any deoxygenated blood, it is pumped through the right side. This is right side, okay, ventricle, and it goes to the pulmonary arteries via the pulmonary valve, and then the gas exchange happens here. The oxygen is absorbed by the blood, and the carbon dioxide is released in the lung, right? Which is taken out by the atmosphere by the ventilation process. So the oxygenated fresh oxygenated blood is brought back to the heart where the pulmonary veins, and then it comes back to the atrium, and this and this cardiac cycle begins, right? So what I was saying is, let me just fix it. Yes. So now in the pulmonary circulation, what is happening? You know that pulmonary circulation, you are actually supplying the blood to the lung. So deoxygenated blood pumped through the right ventricles, right? Right ventricles, and to pulmonary artery via pulmonary valves. Okay. Lung, for the gas exchange is happening through the lung, and in the last one where the gas exchange was happening, gas exchange was happening in capillaries, where, but in the there only the lung is happening, not the nutrients, right? And from the left, here if you see, the fresh blood is brought to the left atrium by the pulmonary veins, from left atrium to the blood to the left ventricles via this mitral valve. So mitral valve is the important point here, and then this. So if I write down what are the important things, so let me just put it here. Let me just make one slide. Slide was here, na, right? So I will be just pointing up some important points that could be important in the examination. Okay, so one is this mitral valve. Okay, and one was what? Tricapsid valve, if you remember. This one, cuspid, tricuspid, right? Okay, so this is it, and also these percentages. Parts at a time. Right. Now let us. So what is this pulmonary circulation, coronary circulations? So if you see this, the part of the blood vessels which are there, so blood supply to the heart is happening through the coronary circulation, and then there is this main coronary arteries lies at the surface of the heart, right? So these main coronary arteries which are the lying at the surface of the heart, these arteries, they supply blood to the heart, and is insufficient coronary blood flow means there is this ischemic heart disease, a very common cause of death. Okay, whatever heart attack or something uh, it comes up into the picture. So if you want me to put one thing over here, and the important points that I am saying is this about this you have to read. Okay, now if you see this here, this main coronary artery lies at the surface. Diagnosis as well as surgical procedures requires the understanding of the flow behavior. So here the importance of this. So if anything you talk about, be it angiography, where this angioplasty happens. So in this one, if you see, this is the stent installation. It required flow behavior. So the knowledge of flow behavior is important in this regard, right? So if you see this, then cerebral circulation is another one where this blood supply happens to the brain. This is the typical flow rate, ml per minute. You can see how much amount is flowing. 15% of the cardiac output. is going to the brain. Too much blood can raise intracranial pressure, can compress and damage brain tissues, right? Too little blood, death of the brain tissue. So, what happens in the high blood? Uh, this intracranial pressure is important. So this you need to be careful with this. 750 ml per minute, 15% of cardiac output. And this is this intracranial cranial pressure, right? So if you see this, if the blood is very less there in the brain, because of any reason, if flow of the blood in the brain is restricted, so the cells which is actually making up the tissue of the brain and subsequently the brain as an organ comes into the picture, they will not be nourished properly and they will be not uh, healthy. The flow of various nutrients, vitamins and various cellular processes which are there in order to maintain the condition and working of the brain, it will be damaged, right? So cerebellar aneurysma, localized dilation or blooming of the blood vessels, right? So cerebral aneurysm, which is localized dilation or ballooning of the blood vessel, right, in the brain. So this is important one, and this is this things. You see, this picture actually dictates about the same. This aneurysm, right? Okay, so coming to the next slide, here heart pumping is explained. So this has been explained very thoroughly. You know that total duration of cardiac cycle is one heartbeat 72 times. So in 1 minute, so 1 by 72. Okay, so one cycle is 72 times, right? And this is the blood as a complex fluid. And this slide was very important in terms of like constituents constituents making up the blood. Okay, so if you see this uh, here, this a suspension of plasma, which plasma is considered as a Newtonian, but blood as a whole is considered as a non-Newtonian, which comes into the picture into the category of the pseudoplastics, right? And if you see this red blood cells, which is called erythrocytes. So these names are also important. Maybe you will just confuse it apart a bit, but please remember this. White blood cells are leukocytes, and this platelets are what? Thrombocytes. And this blood viscosity, which is this Newtonian behavior of the shear rate, this has been discussed, which says this 3 to 4 cp is the blood viscosity, and this various embryology that we are studying how this shear stress is related to shear rate for the blood has been discussed. So you see this 45% of the red blood cells are there, white blood cells are very less, and then rest is the plasma. And platelets, the white blood cells and platelets cover up the just less than 1%, right?
So these were the typical channel dimension within the body, within our veins, inside the body, and these are this the so if you see the minimum one is this 8 micrometer, right? With also the when the diameter is less, the wall thickness is also less. So these are some things about arteries, arterioles, and veins, and often the channels are curved, which is aorta, right? So arterial resistance vessels we call that. Why? Because these are strong muscle walls, alter the blood flow in each tissue according to the need, right? And veins, these are capacitance vessels. Resistance vessels are arterioles, and capacitance vessels are these veins. So this point you remember. So if you see this, the questions that were there in this first assignment, so through the questions if I discuss, then I mean, uh, where is this assignments? Let me just open it. Yes, so this was first assignment. Okay, so first assignment was this largest artery in the human body. Okay, then aorta is that blood is a what pseudoplastic, as I discussed today only. What is the average amount of blood pumped by the human being? 5 liters. Then transport of deoxygenated blood from right ventricle to the lung is what? Pulmonary artery. This is a function of pulmonary arteries. We have discussed it. And then this select the correct statement regarding the surface tension. Okay, so let me just yes. So select the correct statement regarding surface tension. Incorrect statement. Okay. Surface tension is force per unit length, right? So that is there. So if you see surface tension is gamma, which is force length. Okay. So force is what? Newton per length is meter. So it can be defined as the work done per unit area in increasing the surface area. Okay. So it is also defined as gamma equals to W by delta A, or work done equals to surface tension time change in area, right? And this is this standard example of this slider and this soap film, right? The soap film. And when it is changed to some other area, right? Now, what I'm saying is this: if you actually see another question, what is the correct relationship between this kinematic viscosity and the dynamic viscosity? So this is the option is correct one. So I will be just reviewing the questions that has been asked to you in the week assignment, and we will be solving some of them. Whatever will be the tricky, and I will be revisiting the course so that the entire revision kind of thing happens for you for the all the 4 week content that was there. So through questions, if we go, it is much easier for us to actually get the things properly, because we actually like it's humans ability to learn more through questions. Like if you absorb, we absorb more if we are solving question and then stacking and then going to the solution for that. What is the following force doesn't play a role in defining the physical significance of which of the following is not playing any role? So this one is correct one, buoyancy in the gravitation, and then this is this typical Reynolds number for the pipe flow. Okay, so in the pipe flow, if you see from for the laminar, uh, if Reynolds number is less than this, so laminar, and this is transition, and then more than this is turbulent, right? So next one is which of the following statement doesn't hold good for the Hagen-Poisson equation? It can be applied to the Newtonian, it can be applied to the incompressible fluid, can be applied to the to calculate pressure drop for the laminar flow in the channel. So it is right. It is not for the turbulent flow. Why? Because for that this Darcy-Weisbach equation is there, right? What is Darcy-Weisbach equation? If you remember, in the Darcy-Weisbach is HF, which is delta P by rho Z, is 4FLV square upon 2GD, and here this F is a fanning factor. Fanning factor F is equals to 4F Darcy. So these are these basic fluid mechanics. You should actually look at those for turbulent. And in order to calculate this F, this chart is used, right? And if you remember the Moody's chart, you will be actually knowing that. And now this is this Bernoulli principle. On the Bernoulli principle, there is this equation applicable to the Newtonian fluid. What? Can we apply to? So here this applicable to the inviscid Bernoulli. And this is this specific gravity dimension. Here is this one bar is approximately equal to this question on the units and dimension. So Knudsen number for the gas is defined as, so Knudsen number for the gas is defined as lambda, mean free path for the fluid molecule, and D is the characteristic length of the flow. Lambda by 2D, you see lambda by 4D, lambda by 2. So Knudsen number is lambda by D. So in nanotechnology, if you see this D and this lambda is mean free path, which is like difference, the distance between two molecules, between two successive collisions, right? And then this, if you see this D will be very, suppose you are solving a problem where you are actually looking at like this problem flow on a plate, right? And if the layer is very thin, then the thickness H is very less as compared to the dimension L, which is the domain length, right? And this thickness H is far less than lambda. It is very far greater than lambda. So in that case, your height is like very smaller as compared to the distance D. Health disciplines, right? What is diastole? There was two systole and the diastole, if you remember. Diastole results in this injection of the blood to the urethra and pulmonary artery, right? Which is false. It is wrong, and we have discussed the same with very. So stress, Hooke's law states there which of the following quantity represent the resistance flow. How much is the blood on an is 5 liters? So that we have solved it. What is not the role of the blood in the human body, which is this digestion is not the role, right? And then there is this. Okay, so it's done now. And if I go to the slides again, so it's like a bit hang is there. Wait. So, and now if you look at the assignment number 1, okay. So in the assignment number 1, you see questions on the systemic circulation, the pulmonary circulation was there, and there is this regarding the cardiovascular system. Which of the following is correct? Which is responsible for the blood flow throughout the body, responsible for the transport of the nutrients such as oxygen, amino acid, and various organ, do not play any role in the maintaining constant temperature. Yeah, this is wrong. So then responsible for the transport of the hormone from one part to another, right? So let me just, if I can open this in the web, then I can show you a bit. Wait, if I can open this in the web, right? Yes, so if you actually open this, let me just open it. Yes, it is already open, right? So I'm going to the course, and then this is our course. So this is the assignments that were given, right? So this is for fourth week. Let us first discuss the first week. Where is the assignment? Yes, this is the assignment. Like around 20 questions are here. So we will be actually discussing the same. So these two we have discussed. Another one is this is the order. So this kind of question can also be asked like select the correct sequence for the flow of the deoxygenated blood. So the diagram you should remember like how it is flowing. And then this is this right side of the body. And then this uh, coronary artery is responsible for supplying blood to. Coronary artery is supplying blood to heart. You remember. And then what? You see this one, choose the correct answer to fill in the blank. So this is from this plasma, WBC, RBC, these things. And if you see answer here, this Newtonian, RBC, plasma is Newtonian, and this it is also vascular, viscoelastic in nature, which is due to the presence of RBC and WBC. So about the blood, and because of the plasma, at high stress it behaves as a Newtonian. So that is the important point for the blood, right? And one diagram was there I will be discussing. I think I have taken one question on that, right? Then these are some dimension based question on the artery and venules. And then this is aorta. In the aorta the pressure is pulsatile in nature, whereas it is not pulsatile in capillaries. Why? Because this dimension is very less. So if the thickness is very less, thin walled, then that case alpha Mobersley number you can remember it will be very small. Okay, so you please just look at those pulsatile conditions where this we have discussed, right? So these were some of the questions about DVDT, which is the acceleration, some basic questions on the this no slip condition means what. So mostly theoretical questions were there in this particular week, right? Less than 10% of the tube. So thin wall approximation can be applied if the tube wall thickness is less than 10% of the thickness of the less than 10% of the tube radius, right? Not the diameter. You please remember this. It's radius, right? The material in which the material react differently to stress applied in the different direction, which was the one is incorrect. So this solid deformed continuous you can see this is applied over time. No, it's about liquid. No, it's rate, strain rate. So it is done. Now if you move to the next week question, if you see, yes. So in this week we had solved this particular model, which was this cardio Yesunda model, and then on this one, this constitutes 55 to 60% of the blood volume. What are also called erythrocytes, are disc shaped, yes, and then dominates the rheological behavior of the blood. Okay, so these were correct about this RBCs, right? So general questions were there. So one application here is just about the solid basics, solid dynamics, and then what are the factors which affect the viscosity of the blood suspension, concentration of the particles, shape of the particle, interaction between the particle, and the rigidity of the particle. What I think all of them is correct answer. So that is it. And this is on this stress, shear stress versus stress shear rate diagram for the Newtonian. This what I'm saying is pseudoplastic, dilated, and this being gum plastic, right? So A should be pseudoplastic. So this is correct. You see, D is the correct one. What? Yeah. Hypertension is caused by what? Narrowing of the widening, dilation, and thinning, narrowing. So narrowed, so there will be less blood transport, there will be high speed blood transport, there will be low pressure regions created at some places and high pressure regions created at some places. Because of that, there will be fluctuations coming up into the body, and then there will be problems associated with that. So these were some numerical problems on the same, like this one is the capillary viscometer of the length 50 centimeter, the radius 1 mm, having the pressure difference of 740 mm of Hg, calculate the well shear stress. So this is the standard fluid that is there. So we had solved similar kind of problem in the class as well as in the lecture. So please go through them, and you see all the questions are from the slides or from the discussions that we already had. So the calculation of the entrance length, if you remember this about the entrance length, what I'm saying is entrance length was what, which is 0.05 times. So this was this Cassion's fluid where this both the factors has been taken. In the Cassion's fluid, you know this yield stress is required in order to have the beginning of the deformation. Okay, And then this one is this: which of the following is true for the fully developed flow in the pipe? X is the axial coordinate, R is the radial coordinate, U is the axial component of the velocity, and V is the radial component of the velocity. And if you see this del U by del T equals to 0, del U by del R equals to 0, U constant, del U by del X equals to 0. So if you see this uh, for fully developed, you know that with the X, there will not be change in the velocity. So for any cross section, the velocity remains the same for the given streamline, right? So that is it. So this was the week 2. Similarly, week 3 and week 4 was there. So what I'm saying is, let us come to the week 3. So this revisiting will make you comfortable with the questions as well as what are the things important to look at just before the exams. Okay, so this is unable to reach. I think some problem. Yes, see, yes, it came. So this was the lecture about the Wormsley number. And on the spring dash model also this numerical is there. So we have already solved one problem on the spring dash type model for viscoelastic fluid. The dash element represent the viscous component and the spring represent the elastic component, right? Following the principle of the cost function minimization in Huygens-Poiseuille equation, flow rate is proportional to the tube radius raised to the power 3 was the correct answer. So we have already solved some questions on this. Then 10 and 11, consider the following capillary. Assume the density of this, respectively. Assume the heart rate is A. So, so let's. So these were some of the for small Wormsley number. You see del P by del Z and Vz are like they will be out of phase. What I understand. And there will be this sinusoidality associated, so pulsatility associated. So 180 out of phase is the correct one. So on this equations we had solved, we will be looking at some question in our part. We have what we have discussed. Okay, the flow in the capillary is dominated by the viscous effects. Already we have discussed this as the laminar flow will be prevailing in the capillaries because of the low dimension. As we know, it is less than 8 micron, sometimes less than 10, and that micron, the surface effects and the viscous effects dominates, and gradually there will be this high viscous dissipation associated. So Vomersey number alpha square in the capillary is, so in the capillary, as we know, the Vomersey number will be very very less, what I understand. So only C option remains there. There was this comparison also in the lecture, if you remember. Vomersey number sir has calculated for two different diameter tube, right? One was for the capillary and one was, I think, artery or arterial, right? So just look at this. You please look at these questions for 2 minutes. I will be just joining, but before that, let me just put that these question I will be discussing. Let's just put our problem that we had solved in the week 4. That is another thing. So where is that? Yes, week 4. Let me just take this week 4 lecture here. So about systole, diastole, I have explained there that this is the contraction phase of the heart. For the systole, the ventricle contract, pushing the blood out of the artery is the arteriole, and this results in this high pressure systole. So I have just made one. No, this was the, yes, this is the thing I was talking. This, yes, this short forms we I have made. Okay, so you please
So let me just put this question that I want you to solve, and then we will be discussing. Can you please solve this question again? So it will be good for you. Take some time and solve this. I will be joining in a while. Okay. I hope you are going through the question, and then like uh, this particular we have solved, and you see this, which of the following is true for the hoop stress in the thin elastic tube? And if you see this, this was the hoop stress part that we have thought of, and in the lecture you may have seen this hoop stress is same as this circumferential stress, and then h is less than a under that uh, limit. There was some derivation which is this c, you see, where this balance of the force in this lateral direction, so dx into this, this is this dx into 2a c, this is areal into p, which will be balanced by the hoop stress part, and then subsequently it will give you, this is this rho equals to p into a divided by h, right? And so this was straightforward. A, B, C, and E was the correct answer for the same. So mostly I have solved during the discussions the multiple choice questions. Why multiple choice question we have solved?
because there you need more attention. It's not like one option correct. Here multiple options. It's like blend of many MCQs together in one, right? So this was the thing. So if I start to discuss this from the beginning, so let me just put it here or somewhere here. Yes, this. So this was the fourth week of our lecture where we discussed about this Wormsley number, Bessel function, this pulsatile Wormsley number, and how the solution of the Wormsley number considering intermediate value of Wormsley number, by like both terms, which is this inertial term and the viscous term, and also this pressure gradient one and the velocity gradient taken to be the pulsatile one. This turbulence has been taken into account. And then this laminar flow in the steady flexible tube also we had discussed, and then pulsatile flow of an inviscid flow in the flexible tube has been discussed thoroughly. This was the main equation that came after solving the Bessel function, and these were the considerations for doing this calculations in the given scenarios, right? And now if you see this is the difference between systole and diastole. So systole concentration, there will be contraction, there will be high pressure, pumping blood out, high pressure. Diastole, relaxation, filling with blood, low pressure. So in the context of heart, okay. So these were some of the questions that we have solved. What happens during the systole? Which phase of the cardiac cycle has the highest blood pressure? Okay, and then different during the diastole, the heart is which term associated with the filling of the heart chamber? Diastole, systole. Many questions we have solved on the diastole and the systole, right? These were the answers of the same, and some true false question we have already solved. And if you see this, the wind Kessel model also we have seen here is simplified representation of the arterial circulation to describe how the cardiovascular system regulates blood pressure and flow in the particular really useful in understanding the relationship between the systole, diastole, and vascular resistances, right? So in this wind Kessel model, he has actually used compliance reservoir compliance reservoir where the model treats large arteries as the compliant reservoir, which is meaning air chamber, the chamber that store and release blood to maintain continuous flow, right? Even when the heart is diastole, it explains the dampening effect of the arteries on pulsatile blood flow, right? So he has considered the set of arteries, veins, these things, okay, to replace it by the equivalent pipe, and he has calculated different things, okay. So gradient of p versus time, right? So now there could be different kind of Wind Kessel model about which we have solved many questions. There are like two element Wind Kessel model, three element Wind Kessel model, and four element Wind Kessel model. The two element one is consisting of the arterial compliance and the peripheral compliance. Arterial represent the elasticity of the artery, which helps in storing the blood during blood during systole. Systole was what? Systole was what? There is this high pressure situation. Removal is there. In diastole, there was a feeling, right? Does not fully capture arterial wave reflections. So to capture that, this another came, which is three element model, where this characteristic resistance came into the picture, for which actually proximal resistance before the blood enters the arteries, right? More accurate in modeling arterial blood. And the next one was this four element Van Kessel model, where this includes inertance L, where this inertia of the moving blood has been accounted, and where previously the most physiological representation by the but is more complex. It provides more physiological. This what is physiological also we have discussed. So these were the questions on this Windkessel model we have solved. So I will be just putting it slowly so that you actually get a chance to revisit it. Okay. So about pipe flow, flexible tubes, there is this one Mercilli number. In this one, there is this Reynolds number. So one Mercilli number comes when this flexibility of the tube has been considered, and this consideration is actually taken care in terms of like uh, both are inertia force to the viscous force, but here there is this transient inertia as the pulsatility has been considered, the velocity and the pressure gradients are pulsatile in nature, right? So that has been uh, taken into account, right? Now, if you see next one is this true false on the same. There is difference between the flexible and the elastic tube because elastic tubes are the one which strictly follow Hooke's law, which is not necessarily true for other blood vessels. It is true. Okay. So what are the steps for solving steady laminar flow in the elastic tube? So these are the steps. You just calculate these things, which is Vz, Tz. So Vz is calculated through the Wormsley solution. Then use this QP delta P in order to solve this. For steady laminar flow in the elastic tube. So these were the points. So what are the assumptions taken? Wait, this is all correct. Okay. What are the assumptions taken while solving steady laminar flow in the elastic tube? So long and the slender tube. Let me just see if something happened. Let me just see. Yeah. So long and the slender tube, laminar and the steady flow, neglect entrance and the exit effects, right? So let me just delete that so that I can control the meeting also along with the lecture, right? So if I can put it here, I cannot put it here. That's a bit hang is there. So let me just fix it. So it's lagging a bit. Yes, so yes. So this is that. So these were some of the questions that we have already solved, right? So this is the one we are solving. These were the lecture part of the lectures we had already solved. So I was talking about this. So these were the questions that are important. I just wanted you to revisit it. See this one. Which of the following is true for the Wormsley number? So definition of the Wormsley number, and then how the Wormsley number value is different for the capillary and the aorta, a capillary aorta, its transient RE, and how this flow profile, velocity profile using the Wormsley solution for different Wormsley numbers starting from 3.34, 4.72, 5.782, 6.67, right? With the fractional radius position. So by this biodynamic circulation has been explained here, the pressure gradient varies as a cos omega t. So it's sinusoidal, right? And here the plot between this omega t for varying area, it is correct. So all of the options were correct. Where this low alpha means parabolic profile means large, this flatter profile, high alpha, smaller gradient at center. Inertial influences more. The B option, inertial influences are less, viscous influences are more. Why? Because alpha is low means viscous influence is high, as it is inversely proportional. If you see here, it's inversely proportional to the viscosity, right? And so this kind of question can be asked in the exam, right? So this was the one question that I wanted you to be. So in this one, you see accelerating flow is more stable than the SF at given Reynolds number. Okay, steady flow. SF means steady flow, and transient RE for the accelerating flow is higher. True or false? So it's true. Both were the true. So we have already discussed it thoroughly. Please revisit the live sessions that has already been taken. Uh, and this was this. So this kind of numerical problem can also be there. Some expressions you might be actually having some practice on. Okay. So here this what will be the final relation? Okay, between the flow rate Q and a radii if linear relation between the AX and PX is assumed. Okay, so this is has been used when this relationship for this radii of the vessel was depending upon the one Wormsley as a linear one, and following solutions came up into the picture. So all of the questions is correct. So please revisit these. So here the laminar flow in the flexible tube, steady tube, versatile flow, inviscid flow mu zero fluid in a flexible tube, which speeds up there. So we had these solutions also. for the Q. Okay, so this was our fourth week, what I understand. Now, if you go for third week, discussions that was there. So let me just revisit the content of the fourth week which was there. In the fourth week, what are the contents that has been asked? So this, you see, basic definitions were there. So none of the questions are that tough. Everything is discussed in the class, right? For the steady flow in an elastic tube, consider pressure to be linearly varying with the radius. If the flow rate Q varies, which of the this was there in the discussion, so, and is 5. So this one, question number 5, you see we have discussed in our discussion. Where is that discussion? Yes, it is here. So this question number 5, see we have solved this one. So in different way we have solved it, but yes, this option C is related. That's why this multiple correct options we used to solve, right? This elastic tube wave speed. So if you remember this, okay, and then the equation for that, where this omega c square was here, 1 by c square, I think. Now, this one you remember transient boundary layer thickness delta is defined as, so you can look at the unit. So the unit only you can actually pick up the correct option, right? On the Bessel function, property of the Bessel. Hmm. So these were the correct option. I hope you have solved it and you have got the solution of the same. Okay. So this was it, right? Now if I actually take the question that we solved, is here you see. So let me just open the week 3 where we have solved many questions. Yes, in the week 3 we had seen this lots of Winsberg's effect, like climbing up these non-Newtonian fluids on the rotating wall, and then this extruded swell, how viscoelastic model comes into the picture. That basics we have actually seen, and then like bifurcations also we have discussed. So if you see, this was the content that we have already discussed in this. No, just yes. So in this one, this first question was this an oscillatory flow where the Moberly number increases, which of the following increases significantly. So it is all the Moberly number again with the solution you see, and then under which situation the obtaining velocity profile for this motion is similar to the Hagen one. See this. So Hagen one when this laminar flow will be bubbling, and when it bubbles when the alpha is very low, right? Then so option B is correct answer, right? These were the profiles which came into the picture, and here you had this flow reversal. Sometimes flow is moving forward, sometimes moving backward with 180 degree of phase, right? Phase difference. So that is the thing. Uh, and now we just put here. Yes. So alpha is also defined in terms of oscillatory inertial force to the viscous force, right? So in that case, the way it has been defined, it gives that cube radii versus oscillatory boundary layer thickness, and that boundary layer thickness, you see, it only depends on this kinematic viscosity to the kind of frequency at which the pulsatile flow is happening, right? And this is the final reduced after the order of magnitude analysis. This is the final expression which actually dictates the inertial influences where this temporal term has been taken into account, and then pressure drop, and then this viscous dissipation term. Okay, so another question was this: which of the following profile relation of the following differential equation? Correct solution for the following differential equation, right? So all the questions that has been taken and discussed during the weekly discussion sessions, what I think is I hope you have learned many things out of that, right? And you have got to learn and where to focus, where not to focus, what are the things you should do, and it was like interacting throughout, right? So maybe this lecture schedule was a bit uh, random. I say as none of you is here, but what I think is these recordings will be there and you will be getting benefited out of this. You can watch at your pace. And anyway, all the four lectures, this is combination of all the fours together where I will be actually recapping all the concepts. Meanwhile, discussing with the lecture notes and then the questions. And also here, that's the new things here. I am also discussing the assignments which was there for the 2025. So what I observed that whatever questions are given to you in the assignment that are uh, much difficult or equivalent questions we have solved in this live session, so that should not be problem or difficulty in solving those, right? So this was the solution for this lower alpha Robertson number where this viscous dissipation is very high. Okay, viscous diffusion, right? So, so if you see this, I will be actually looking at this. In which field is the Robertson number is most? So this is very straightforward. You see this in this arteries or vein. Here the plasma, WBC, RBC, platelets, these are going, right? And proteins, amino acids, everything is going. Because of that, there is this. Uh, this discussions are going on. Like this transport of these species around the body is up, right? So another question was for the blood flow in the small capillaries, the Robertson number is generally. So the value it has been asked, and you see different dimensions we have discussed on, right? So see this for the 5 to 10 micrometer, very confined diameter is very less. And if you see this microfluidic domain assumed to be laminar, so here this oscillatoriness of a viscous force, this R is under root of omega by nu, which is the kinematic viscosity. What does Marie's law describe? It is the optimal branching ratio of the blood vessel for minimal energy reception. This also we have discussed. We had solved this particular numerical. Parent to that, this is the solution for the same. So lots of problems we have solved. All around I think 100 problems we have solved. And we have discussed during the 4 sessions of the problem solving. Along with that, we have sometimes discussed the content and the assignments which was there in this given to you weekly. So I was not supposed to explain solve the assignments during the weekly sessions because it was for you and evaluation is based on that. But what I do think, I mostly took a similar problem or somewhat much difficult problem than the problems are being asked in the assignments, right? So coming to the next problem, so here you see this one. So about the boundary layer, at the bifurcation we talked about, and then there is some flow separation zone, there is also flow reversal zone, and why the plague is also actually forming over there. So there was few articles on this like plague formation and on the constituents of the plague, and why this plague actually comes into the picture. If I just search is constituents of plague, right? So let us search constituents of plague. So like cardiovascular plague, cardiovascular. So the plague which is there in the blood vessels, right? So it's like fat, cholesterol, calcium, inflammatory cells. It is saying that. So it's from this heric origin. And if you see this, the plaque is composed of fat, cholesterol, calcium, and the inflammatory cell that built on the inside the body interior arteries, right? Over time, this plaque buildup hardens and eventually narrows the opening of the arteries. So you see, the effective diameter is now less. Okay. So if you see the side view of this, let us look at these images. So if you see the side view of this, wow. So it looks like this, right? It looks like this. So how this plaque is forming, growing, and blocking the interior, right? So okay, so there are different images. So these are the Wikipedia and Google search. I should already happily acknowledge these links where we are going. So it's for educational purpose, so we can go through and we can actually learn something out of that, right? So the next problem you see, so we have discussed many things together with that. So if I tell you how these discussions were made on this, so let me just, the plan was there for this course, and then how this plan worked on. Like this an introduction to cardiovascular fluid mechanics by Professor Raghavendra sir. Here this the main course, this provided an overview on the important problem in the human circulatory system. The course would provide introduction to the cardiovascular system and what and uh, important fluid flow.
problems in large arteries, right? The goal is to provide the student with the necessary background to apply the knowledge of the fluid mechanics to analyze the flow behavior in the biology system in general human systems. It is hoped that this course would be able to develop a perspective towards this. Okay, so what I think, this was the agenda with which with what I have started. I think I have shown some of the the things to you. Okay, and now there is one new research came out, like one webinar is there on YouTube, and that is a bit related to the course content of us, and it is very important if we actually go through that once as a part of the course only. So so I should definitely acknowledge her, uh, and I will be just putting that link also in today's slide. Wait, I will be first putting it here, and then I will be discussing the main contents that has been discussed over there, right? So let me just see cardiovascular fluid mechanics, right? So you see this one. So here, this one is the important lecture that I was talking about. It is given by Stan. Let's mute it. I will be discussing anyway these things, but this is the lecture, an important lecture related to the course content. Let us just put it here with the title of the course, which is this. Okay, so this is the link. Fluid mechanics of the cardiovascular system, interesting impossible problems in the biophysics and maths, right? So if we actually discuss of the same, okay, so what is there is this one. If you see, leave it, yes. So the basic equations of motion that are important, that we also discussed in our uh, lectures, basic fluid mechanics. There are different requirements for solving this Navier-Stokes, which is actually kind of taking care of the fluid flow inside something. So in this case, we are actually working on these cardiovascular systems. So accurate geometry, boundary condition, fluid model, robust numerical solvers, and good grid. These are the important aspects of that, right? And if you see this here, if I tell you, so these were the content you see, veins, arteries, and heart. Where this cardiovascular system is what? Goal is supply of the blood and oxygen and the removal of waste. Heart has the two part in the parallel, which is the right heart supplies sun and left is supplying to the body. Flow path, heart, arteries, capillaries, vein, heart. Again, heart, from the heart it goes to the artery, to the capillaries, to the veins, and then to the heart. And then vascular looks like a tree. Large vessel aorta 2 centimeter, small is the 10 micrometer, right? And if you see, this is, yes, this is the one. Why study of the fluid mechanics of the blood is flow is important is that there is this different people develop vascular disease in the same places, right? Uh, the only thing unique about these vessels is their shape and the flow inside them. So so if you see this different zones where this serratine bifurcations, coronary arteries, cerebral arteries,
rental arteries and this abdominal aorta. Everything is located somewhere near it, and then these are the central system of the of our body, right? So if you see this, there is one study which is on this cardiovascular cells respond to the blood flow to flow, and where this was there this on the inner surface of the blood vessel, they have grown these endothelial cells, and then they have observed that these two things, like when the oscillatory and the unsteady flow was there, then the morphology of the blood, these endothelial cells look like this, and in the steady flow, their morphology was there. So from these images, it is the reference is given over there. So it proved that this. Endothelial cells or the cells cellular walls do affect the flow behavior, and also the flow behavior do affect the arrangement of the cellular system, which is actually intact, making the entire system intact, right? So so now if you see this, so what can we learn from studying cardiovascular flow? So, early diagnosing of the cardiovascular problems can be done where when and where the way disease will be developing, and how this the life cycle of the disease, how it will be worsening, what precautions we have to take, and then this drug delivery planning. So how everything will be done in terms of like doing the medication to the for the disease at the particular place, and then where does medication end up if you inject it randomly. So that the close prediction can be done. Smart devices such as stents, then LVADs, and then infusion pumps. These are also their designing and improvements can also be supported if the knowledge of the fluid mechanics will be there in place, right? So, so it's from the Tufts University School of Engineering. So like anyway, this was very much close to our course. That's why I am actually discussing the same, right? So we discussed today the assignment that was there to you, given to you in the 2025 assignment section, and also whatever content I have talked in the last 10 to 20 minutes. I am actually basically dictating you this particular thing. You do watch. This is very informative, well explained, and this presentation skills also you have to learn, because that is the most important thing. And at the end, uh, how your research, your learning is actually helping the society in some sense is the importance. The key aspect or the key thing uh, for out of this course, the takeaway or uh, message out of this course is you have to be solving some problem which will be directly or indirectly impacting the humankind, right? Then the real agenda or the real motivation of the course will be full-fledged, right? So so cells response to the flow motive. So it means we can't tell which endothelial cells are healthy without cutting a patient's open, okay? So research question is, can we tell how whether cells are diseased and how that disease will progress by looking at the cell at the flow, right? Can the flow morphology will be connected to the problem which is residing inside the human body or the patient, right? And then long-term goal is take basic non-invasive flow measurements, use them to determine whether the disease is likely to develop and where where it will develop, right? So now there is this cell response to the flow. There was this experimental setup. You see, there is the cone, there is the base plate, and this HUVCs are there. So motor force cone to rotate at a time varying speed, right? And then fluid in a gap is seared at a time varying rate. Then human umbilical wean endothelial cells feel shear force, and that was the diagram that we were actually. So it's like there is this UR, this is the base where this is R, and then there this is the HR height. So that has been used, and then cell response to the flow where this aneurysm flow waveform and then healthy ultra wave flow waveform. So in the problematic condition, in the normal condition, so red is this cell junction marker where we're gathering they have used GFP, they have used for cytoplasm marker which is green, and blue is DAPI which is nucleus marker. DAPI is nucleus, GFP is for this, and regathering is for red which is cell junction marker, right? So here you see this, they have devised it as this healthy flow waveform, unhealthy flow waveform, right? And based on that, you see for different eccentricity ranges, they have seen the percentage of HUVECs which was there, right? So the next part which has been explained is you see this oxygen transport in AA, the abdominal aortic aneurysm. Aneurysm we have already seen there is this bulging. So bulging in the brain also there was some aneurysm, very common in the adult. It holds you are fine, it bursts, you die. Okay, so it should not happen. Flexible via major surgery need to be identified high risk cases. Some evidences that bursting correlates with is thrombus buildup. Some evidence that the bursting correlates with is oxygen starvation in the walls. So there could be this thrombus can also lead to the bursting. Okay, and now let us see the next part that we will be going to discuss is. So this was very informative one. So now the research problem based on this erythras, the one we were talking about, abdominal aortic aneurysm is we can't identify which aneurysm, abdominal aneurysm, and aortic aneurysm are likely to burst. So researchers can we identify problem aneurysms by simulating oxygen transport to the vessel walls in AAA. Okay, so this was the question that they solved, and they came up with some. It is not there. Yes. So lumen is there. You see flow scale, advection, convection, and then thrombus is here. No flow, scalar diffusion, and then this walls. No flow scalar diffusion with concept. So oxygen transport has been mapped properly, and they have seen the pressure, oxygen pressure, and then the flow velocity, different cross section, right? So if you see this, if the tumor is there in the lung, which is EPR tumors, EPR in the lung tumor, so tumor exhibit enhanced permeability and retention, enhanced permeability and retention, which is EPR, increased nanoparticle uptake from bloodstream compared with the healthy tissue, right? So chemotherapy can be carried by the nanoparticles where this EPR varies from the tumor to tumor, which is this enhanced permeable retention, right? Retention. Possible contributing factor weird lumpy vasculature trap pockets of flow and the particles, right? So these were some flow velocity versus oxygen pressure flow fields and about this EPR. So based on that EPR problem, we could use EPR for chemotherapy dosing, but we don't know how much EPR a particular tumor has. So can we learn something about magnitude of EPR from the geometry and the flow in the vessel? Use flow data to calculate EPR and set chemotherapy doesn't dose that kills cancer but spares healthy tissues. So don't kill the healthy one. So these were the sections. You see how these sections have been taken. Okay. So it has been the model of the heart, almost similar to the heart they have made, and they have modeled it. So how this research is going on, you see. So nanoparticle concentration after 6 hours of the flow compared with the mean concentration. So other area of the interest is flow sensitivity to vessel shape and inlet conditions, coupled flow, solid mechanics simulation, and then this shape markers for the tumor vasculature. Another body flow, breathing, tucking, CSF flow, fluid in the joints, and then drug targeting etc. So these are some of the motivations that are there out of this course. So this entire course actually taught you open cross-cutting problems in the cardiovascular fluid mechanics are hard to measure many things that affect fluid mechanics of the blood flow. Few examples: vessel wall properties, genetics, patients, stress level, emotional stress, and then this flow resistance posed by the vessel network. Model must ignore most important factor, otherwise they are too complicated, hard to tell what is okay to ignore, maybe different for different persons, right? So it's like more personalized one. So modeling long-term disease effects is complicated because there are too many time scales. Cardiovascular disease development around more than 1 year it takes. Cell morphology change 1 day. Cardiac cycle once again. Turbulence milliseconds, microseconds. So how do we put these all together and not break the computer? Okay, so that is the problem. Computationally, it's very costly. Flow are patient specific. So goal is to learn about blood flow in individual unique humans. No control, no repeatability. Individuals are different on different days. Poor validation prospects and very hard to tell what flow features are universal. So or different patients, different kind of things are happening, right? So, like many contradictions in the literature, like paper one is saying high CR rate is correlated with the stenosis development. Some is saying low CR rate is correlated with the stenosis development. So no one does large scale statistical significant study, right? So because of that, difficult to identify and validate data. Valid data interpretation of the data if everything is in the high quality peer review journal, and then difficult to identify what variation in data are due to the different patients having different flows. Patients like to patient variations are not private. Difficult to know what conclusions are generally enough to apply to elsewhere, right? So like another one is hard to visualize and interpret data if not uh, captured, right? Not so. So like whatever medical doctors are there, flow fields are very complicated and very subtle in nature. So its ultimate goal of this field is to generate data that doctors can use. So doctors are not having any fluid mechanics training, so that's why it's become very problematic for them to actually visualize the data. current commercial software reduces flow field to one or two numbers, I am skeptical that this captures the important flow features. So that is another aspect that has to be looked at. So this was a general video that I have discussed a bit. I hope invite you to watch that. That is very good, and we thank them for this particular talk. She was this Erica Cameron with Tufts University. So that was the seminar from her. Okay. So till now we have discussed many things about the course content, and what I think now it's time to just revisit uh, the 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 course transcript finally, and then close the sessions. I hope these all discussions, lectures have helped you in some sense, and you benefited in terms of learning the subject, right? So now we will be going to the lecture 2. Okay, lecture 2 is what, 22. So let's go to 22. Almost 22 is this one. It's 222. Okay, so let us put it here. So fluid mechanics problem of the interest. Here there is this flow in the curved tube is there, pulsatile flow is there, flow in the flexible tube is there. So all these has been discussed in this entire course, right? Flow distribution, the network of tubes, and then this rheology of the fluids. Let me just fix it up. Okay, so these deformations, everything. So about this cantina, fluid mechanics have started with this one. This lambda is less than d. Quantum approximation mean free path is very less than the scale of the problem that we are working on. So for this quantum, our lambda is very Newton's number is very less than one, right? Cauchy stress, these are all the forces acting on the volume. So you see these has been discussed thoroughly. So let us revisit all the slides so that we are actually completing up. So it will be reminding to you that yes, everything is covered up. So let's, yes, so Reynolds transport theorem has been discussed. Mass conservation, see, balances has been done. Using that, momentum conservation also completed. Material derivative has been defined, covering this temporal and the spatial conversion acceleration and local acceleration terms. This is also called the substantial derivatives. This local conversion term has been taken into account. This is the momentum conservation. This flow field velocity and the pressure, and also this the constitutive relations where this Dilatational viscosity, dilatational viscosity, K 0 for the monoatomic gases. Okay, has been explained. Different terms of the Navier-Stokes. So let me just drop it down. So fluid continuum, Eulerian to Lagrange description of the fluid, the Reynolds transport theorem, and the mass and the momentum equation has been explained. In the solid mechanics, starting from the elastic material, discussion started about the stress, strain, the elastic moduli, which is also called the Young moduli. Okay, and then various thing about homogeneous and isotropic material. Something about this true strain versus the incremental elastic modulus, Poisson's ratio, and how this transverse strain, the axial strain, gives different Poisson's ratio for the stresses correspondingly in direction x, y, and z with the given elastic moduli, and how this here stress and the strain is related with each other. All the strains has been calculated and related to the shear stress. And now the change in the polar coordinate happened because this blood vessels have been considered in the radial coordinate system in order to have the clear picture of three dimension. Okay, so that is it. So generalize Hooke's law, stress in terms of strain. So you see all the EX, EY, EZ is there. And we had also had discussion on this that if nu is half, then AX becomes infinite, which means it's zero, then infinite, which means like perfect solid like behavior, there is no deformation at all, right? Bulk modulus of elasticity has been explained and derived. Thin walled cylindrical tubes, and how these thin walled cylindrical tubes are defined with the hoop stress, longitudinal and axial stress has been defined. Thin walled derivation for the hoop stress, derivation for the circumferential stress. Now the hoop stress is related to, now the thick wall came into the picture. For the thick wall, the relationships has been defined, derived thoroughly, all the differential equations taking care of those. Now the rheology of the blood came into the picture, where this rheology of the blood has been explained along with the standard rheological property that was there. Different type of non-Newtonian fluids, shear thinning, shear thickening, Bingham. I think in the second week I have taken this also in great detail. Orthoxotropic, geopectic. Okay, so I think this was this Bingham, and then shear thinning, shear thickening, and power law model, and how this shear thinning, shear thickening is related to the exponent, which is also called D-Valley model. Carey-Hudson model, Berkeley model, Cousins fluid. On this we had many questions, and then rheology of the suspension. Okay, Einstein relations, rheology of the suspension, rheology of the suspension, and then this summary, where this time dependent non-Newtonian behavior, rheology, suspension, and G has been discussed, where this blood elastase, shear thinning, and then this viscoelasticity has been. So about the morphology of the blood, what it contains, like plasma, protein, blood clotting, sugar, lipid, vitamin, hormone, enzyme, and antibodies. Everything has been discussed. Plasma, red blood cells, shape of the red blood cells we have already discussed properly. Erythrocytes, aggregates, what happens at the high CL, low CL with the blood. WBCs, head layers, viscosity of the blood. High CL rate blood behaves as an union, so droplet, right, at high CL rate and tend to aggregate, right, which is this. Rayleigh and aggregation determines the viscosity of at the lower flow rate. So that has been discussed. Low shear, yield stress, tube size, and this blood velocity. Various effect, which was this: if the diameter of the capillary is less than 0.5 mm, RBC concentrated decreases with decreasing diameter, right? Which is called various Lindquist effect, right? Viscosity decrease in the capillary diameter, various effect. And everything has been discussed properly. So, what I think this course entirely covered up the basics related to the the fluid mechanics not required for addressing these cardiovascular problems. And I hope you have learned something out of this course, and this had enriched your knowledge in terms of like fluid mechanics knowledge. Maybe you will be having before, but now this how this fluid mechanical knowledge is used in biological systems. Like this is this another this mechanics comes. This course is a part of biofluidics. Uh, like whatever biological processes are happening, these are nothing but this mechanics, like fluid mechanics. Everything is transport of one thing: heat transfer, mass transfer, fluid mechanics, fluid flow, nutrient transport. So that has been dealt in deep. So thank you so much, and I hope you have learned something out of this. And so it's time to just complete the session. And thank you so much. Thank you, everyone. Thank you.